All right, we are back. This is the part two of our UAV accuracy discussion, and we were wrapping up part one when we were talking about how to check accuracy. And I was showing you this graphic about conducting your flight lines, doing cross flights, and then controlling it. Right, so that's all part of flight operations. Then once we have all that information, right, we want to go about checking it. And that's where checkpoints come in. So we distribute checkpoints across our area and do a statistical evaluation so that we can make an authoritative statement about the vertical and horizontal accuracy associated with our data. Now, these checkpoints are kind of important. And there's a whole set of guidelines that goes into what governs good checkpoints and adequate checkpoints for doing this kind of statistical assessment. So all of the digital standards from the NSSDA 1998 forward say the same thing, right? Which is you have to have 20 points. You can't do an accuracy assessment and expect to get a 95% confidence interval on anything with less than 20 points, right? In general as well, a couple of other rules or guidelines are that checkpoints need to be collected in open, flat areas, right? We're collecting these checkpoints to be reference data. And so we want to collect them where we expect our data to be of the highest integrity. And so slope data, data with vegetation, we expect to get a lower accuracy in those areas anyway. And so for consistent checkpoints on the specifications and the tables that we talked about, we're talking about open, flat terrain, right? And then the distribution of those checkpoints is important, right? They can't be too close together. That's governed by the overall size. We sort of take a measurement of the longest axis of our project area, divide by 10, and that's the distance apart, minimum distance apart that the points can be. And we have to distribute those points around our project area so we don't skew or bias toward any one corner or any one area. So at least kind of divide nominally up into quarters and put at least 20% of the points in each quarter, and that leaves us a few extras to distribute around so long as they're not within 10% of the total longest axis of each other. A couple of other kind of bullet points here. The NSSDA gives us that 20-point requirement. That means that if 1 point fails, we still can achieve a 95% confidence on the remaining data. If we're talking about large areas, both FEMA and ASPRS recommend that we do 20 points per land cover type. So a typical FEMA LiDAR collect might have 100 points, 100 checkpoints in it. The USGS recommends that we assess specific land cover types if those land cover types are greater than 10% of our project area. They're typically talking about larger areas than a drone might typically collect. So, regardless, for a drone collection, we're talking about a minimum of 20 points. And we have to remember that those reference points have to be 3 times the accuracy of our target, right? So the final comment here is that even if our data meets the accuracy specs and we test it and we show statistically that it meets the accuracy specs, that's not necessarily the equivalent thing of saying that we have high quality data. And we can still have sporadic areas of poor quality in our data, or we can have one corner which is completely off, and we can have things that are going on. Statistically, we still meet the spec. Right? And that's happened a number of times where we've had data where either the client or the surveyor has concerns about the quality of the data in specific areas. And we demonstrate that, look, statistically, the data is good. Right? Now, there may be quality areas in specific parts, but meeting the accuracy spec doesn't necessarily equate to overall quality in the data. Let's finish up this talk by looking at a case study and looking at the relationship between points on the ground and overall accuracy metrics. So this is a hay farm or a hay field out just west of, actually just east of Pittsburgh. And we use this as kind of our test ranch. You can actually see snow on the ground there a little bit in the image. And put a whole bunch of points all over it, distribute them, and just wanted to kind of test all of these ideas. So we knew we needed an N, or a total number of points, more than 20. So in this case, we used 34 points, spread them around, 20% distributed, in each quarter at a minimum. Right? And that would allow us to use up to 14 points for control, which we thought 14 is kind of reaching the upper limit, and still have 20 left behind that we can save and use those as checkpoints, as independent checkpoints. So we made sure that they were evenly distributed and had appropriate distance according to the specifications. And just a quick reminder before we start crunching the numbers, right? So this is the difference between the mean and RMSE, right? The mean, or the average, is just the average of the differences, right? And I've seen surveyors and even non-surveyors using the average as kind of their metric for how good the data is, which is fine. It's a gut way of figuring out, how good you are, but it's not the statistical check that we want, right? We're looking for the RMSE, which is the square root of the average, right? Or the square root of the mean of the squares. And by squaring them, right, we can remove whether they're positive or negative, right? We're getting the absolute value. If we just take the average, right, we can have really bad positive, really bad negative, take the average, get 0, and say, look at that, we got zero error, right? So we don't want to just take the average. So the numbers that we're looking for are these numbers on the left, the 10 centimeter or the 5 centimeter. You remember, for vertical data, the 10 centimeter accuracy class corresponds to 1 foot contours, and the 5 centimeter accuracy class corresponds to 6-inch contours. So that's really what our target is. That's what our goal is in determining how good our data is vertically, right? And so that's kind of the holy grail down there, right? If we can get down to 15 hundredths, right, or 16 hundredths, we're good to go, right, for 6-inch contours. So first thing we did is just process the data without using any control, using the onboard GPS, right? Onboard GPS solution, just to see what that would give us, right? And it gave us pretty crappy data, right? We're off by 7 feet. So then we start adding in control, and we used 14 control points distributed around, and we played around with some different scenarios, but we used 14, saved back 20 to do our statistical check, right? And that got us down. Hey, we're getting down using traditional ground control into the 10 centimeter range. So, this, to me, close enough. I can call this good enough for 1 foot contours. So we're meeting, or right on the cusp right there of that 10 centimeter accuracy class for 1 foot contours using traditional GCPs. And that required, that was using 14 control points. Now, if we use our PPK solution, right, we wanted to try out a couple of different techniques. This is what we call the 3-point method, whereas if you use the landing pad for the drone as one of your points, because it can just come up, take a picture of it, right? So use that as one of your points, and then take essentially 2 other targets and just toss them to the left and the right, and it's kind of like an isosceles triangle, relatively close together, given that we might not have access to the whole site, but we could at least put down an anchor of 3 control points. What would that get us, right? So that's getting us better, right? We're down into the 7 centimeter accuracy class here on this test. And then our third test, we said, well, we'll use the enhanced 3-point method. If we spread those 3 points across the terrain so that we're getting the high points and the low points, right? So we can at least kind of get the 3 points distributed. What does that get us? And now we're getting down under the 5 centimeter accuracy class. So using PPK post-processing and enhanced 3-point method for GCPs for control, right, we can achieve, for the exact same flight, exact same data, we can achieve 6-inch contour standards. All right, couple review things, right? 4 final factors. Targets, not all targets are made equal, so be diligent about how you use your targets. Camera calibration, most cameras are going to have some sort of float, and it's a good idea to have your camera calibrated initially And then depending on use and conditions, getting it recalibrated periodically, right? You can still produce scrappy data with really high-end, expensive equipment, right? And that goes back to principle number 1, right? Accuracy is the result of diligent planning and hard work. And then finally, understanding principle number 3, which is the error budget. Right, the entire drone system contributes to error. Right, understanding principle number 3, and then looking at each one of the components and doing due diligence and your standard operating procedures to try to minimize error and reduce error in each one of those components is going to be the key to your success. So, principle number 3, it's the entire system. Right, and here's my reminder bullets of what those components entail in the system. We're talking about the airframe, the sensor itself, the targets, doing diligent flight planning, and then flight execution and piloting, and then doing an appropriate GCP plan and the method of your GCP or your method of control, whether you're using GCPs, PPK, or RTK, and then how much control you have over post-processing software and procedures. That's the end of this talk. Appreciate you downloading part 2. There's the URL on the bottom if you want to download any more of the handouts for this talk or any more of the presentations or materials that we have there. So all the technical references and all the standards are there as well. So appreciate your time and have a good rest of your day.